You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Identity is the cornerstone of application security, enabling both user-to-application trust and service-to-service communication. In the cloud, identity management goes beyond login screens. It defines how applications establish who is calling, what they can do, and for how long. Token handling becomes the mechanism that enforces these guarantees. Without robust identity and token governance, even the most carefully designed APIs or applications are vulnerable to impersonation, privilege escalation, or replay. The purpose of identity and token handling in this context is to deliver authenticated assurance that requests come from valid entities, and authorized confidence that those entities are only granted what they legitimately require. For learners, this domain illustrates how modern frameworks such as OAuth 2.0 and OpenID Connect have become essential standards, creating a foundation where identity, permissions, and tokens interlock to protect distributed cloud-native systems. Application identity spans both human and machine contexts. On the user side, authentication ensures that individuals can securely access cloud-hosted applications with confidence that their identity is verified. On the machine side, services and microservices authenticate to one another to preserve trust across distributed systems. A payment service calling an order system, for example, must prove its identity and scope of access just as rigorously as a user logging into a dashboard. Trust establishment, therefore, applies to every interaction, human or automated. This consistency prevents weak links, ensuring that identity assurance is a universal property across the entire application landscape. OAuth 2.0 serves as the backbone framework for authorization in modern applications. It enables delegated access by allowing a user to grant a third-party application permission to act on their behalf without exposing credentials. For instance, a user may allow a calendar app to read their events stored in a cloud service by issuing a scoped token rather than sharing their password. OAuth decouples resource owners from direct credential sharing, reducing risk. Its flexibility supports many flows, adapting to mobile apps, web clients, and machine interactions. OAuth has become a cornerstone because it aligns with cloud principles of least privilege, scoped access, and temporary delegation. OpenID Connect extends OAuth 2.0 with an explicit identity layer. While OAuth governs authorization, OIDC adds authenticated user information by introducing ID tokens. These tokens carry claims such as user identifiers, email, and authentication context, allowing applications to confirm who the user is in addition to what they are permitted to do. For example, logging into a SaaS platform with a Google account relies on OIDC to transfer authenticated user context from the identity provider to the relying application. This extension bridges a critical gap, making OAuth not only a delegation framework but also a standardized method for single sign-on and federated identity. Roles within OAuth and OIDC flows are clearly defined to maintain separation of responsibility. The resource owner is the user or entity granting access. The client is the application seeking access. The authorization server is responsible for issuing tokens, and the resource server enforces access using those tokens. Each role has its own responsibilities and trust boundaries. For example, the authorization server should never expose refresh tokens to resource servers, ensuring clear isolation. Understanding these roles clarifies how tokens move between parties and prevents confusion about which system enforces which control. Grant types define the ways in which tokens are issued. The authorization code flow remains the most common for interactive users, providing a secure back-channel token exchange. The client credentials flow enables machine-to-machine access with no user involvement. Device authorization supports scenarios like smart TVs, where constrained devices rely on user approval via a secondary interface. Refresh tokens provide long-lived access by enabling renewal without repeated logins. Each grant type balances usability, security, and context. Selecting the correct grant type is a key design decision, shaping how identity and access are handled in practice. Proof Key for Code Exchange, or PKCE, strengthens public clients that cannot store secrets securely, such as mobile or single-page applications. PKCE adds dynamically generated codes to authorization requests, preventing interception attacks on the authorization code. Even if an attacker captures the code, it cannot be exchanged without the associated proof. For example, a mobile banking app may rely on PKCE to secure its OAuth code flow, ensuring that tokens are only granted to legitimate clients. PKCE demonstrates how standards evolve to address real-world threats in application contexts. Scopes and claims define the granularity of access. Scopes express what the client is requesting, such as read contacts or write L payments. Claims convey attributes about the subject, including roles, identifiers, and context, such as device trust level. For instance, a scope may allow reading calendar data, while a claim specifies that the user belongs to the finance group. Scopes and claims together provide both breadth and depth, enforcing least privilege by restricting what actions are allowed and tailoring access based on who the requester is. Proper scoping and claim validation prevent overprivileged tokens that attackers could exploit. Token types serve different purposes in application flows. Access tokens are presented to resource servers to authorize specific actions. Refresh tokens enable continuity by requesting new access tokens without user re-authentication. Identity tokens, unique to OIDC, carry authenticated context about the user session. For example, a client app may store an ID token to personalize a session, while using access tokens to query APIs. Differentiating these token types ensures that applications do not misuse tokens outside their intended scope, preserving both security and design clarity. Token formats determine how information is represented and validated. Opaque tokens are simple identifiers, requiring introspection at the authorization server. JSON Web Tokens, or JWTs, embed claims in a signed, base 64 encoded structure with headers, payloads, and signatures. JWTs allow stateless validation by resource servers, but must be managed carefully to avoid excessive lifetimes or exposure. For example, a short-lived JWT can validate access quickly, but revocation requires careful planning. The choice between opaque and JWT formats involves trade-offs between centralization, scalability, and revocation needs. Token lifetime policies play a vital role in reducing exposure. Short-lived access tokens limit the window for replay attacks, while refresh tokens must be rotated and monitored for reuse. Reuse detection invalidates compromised refresh tokens before they can escalate. For instance, a 1-hour access token paired with a rotated refresh token ensures balance between usability and resilience. Rotation reduces the risk that stolen tokens provide indefinite access, making token handling a dynamic rather than static control. Token storage strategies differ by client type. Browsers must avoid storing tokens in insecure local storage, where cross-site scripting could steal them, instead favoring same-site cookies. Native apps must secure tokens in oxygen monosulfide-provided secure storage. Server applications can store tokens in memory or encrypted configuration stores. Each choice involves trade-offs. Cookies provide resilience against XSS, but must defend against CSRF. By tailoring token storage to client context, organizations prevent accidental exposure of credentials. Session management ties together tokens and user experience. Idle timeouts, absolute lifetimes, and re-authentication policies must align with risk. For example, a high-value financial application may require re-authentication every hour regardless of activity, while a productivity app may allow day-long sessions. Balancing friction with protection ensures that sessions are usable but not exploitable. Proper management also defines when tokens should be invalidated, preserving coherence across distributed systems. Audience and issuer validation ensure that tokens are presented only to the intended relying service and were minted by a trusted authority. Each access token includes an audience claim, which must match the resource server, and an issuer claim, which must match the authorization server. For example, a storage API should reject tokens issued for unrelated services. Without strict audience and issuer checks, tokens could be replayed across boundaries, undermining trust. Mutual TLS and demonstration of proof of possession go beyond bearer token models by binding tokens to clients. In bearer models, possession alone grants access. If stolen, tokens can be reused. With MTLS, tokens are usable only by clients presenting valid certificates. With DPoP, tokens are tied to specific public keys, preventing replay on unauthorized devices. For example, an attacker stealing a token cannot use it without the private key bound to DPoP. These methods elevate token handling from passive checks to active proofs, significantly raising the bar for adversaries. Consent and user experience are essential in maintaining trust. Authorization flows should present clear, predictable prompts explaining what scopes are requested and what data is accessed. For example, a calendar app requesting read contacts should clearly show this scope to the user during consent. Confusing or overly broad prompts erode user confidence and may lead to unintentional overexposure. By making consent transparent, applications reinforce that security is not only technical but also relational, maintaining credibility with users. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. The authorization code flow with OpenID Connect is the gold standard for interactive user authentication. It separates the front channel interaction, where users authenticate with an identity provider, from the back channel token exchange, where the client securely retrieves tokens. This design ensures that sensitive tokens are never exposed in browser URLs, but remain confined to server-to-server communication. For example, when a user signs into a SaaS application with Google, the authorization code flow issues an authorization code to the client, which then exchanges it for ID and access tokens. By combining OIDC with this flow, applications gain both authenticated identity context and scoped authorization in a secure, structured manner. The client credentials flow addresses machine-to-machine interactions where no human is present. In this model, the client presents its own identity and securely obtained credentials to request a token. Tokens are issued with narrow scopes and short lifetimes, ensuring that automated processes have only the access they need. For example, a backend microservice may use the client credentials flow to authenticate with a metrics API. By avoiding shared passwords and long-lived secrets, this flow enforces least privilege while still enabling automation. In cloud-native architectures filled with service-to-service calls, client credentials flows ensure scalable trust without sacrificing control. The device authorization grant accommodates constrained devices such as smart TVs or IoT hardware, which cannot easily present login forms. In this flow, the device displays a short code for the user to enter on a secondary interface, like a smartphone or browser, where full authentication occurs. Once approved, the device is issued a token to act on behalf of the user. For instance, a streaming device may display a code that the user validates through their phone. This flow balances user convenience with secure delegation, ensuring that even devices with minimal interfaces participate in trusted identity flows. Refresh token rotation is one of the most effective defenses against token theft. Instead of reusing the same refresh token indefinitely, each use returns a new one and invalidates the old. If a stolen refresh token is replayed, detection systems recognize the reuse and terminate the session. For example, a mobile app may refresh access tokens every hour, with each refresh token valid only once. Rotation reduces the persistence of compromise, ensuring that attackers cannot quietly extend sessions. It also provides an audit trail of anomalies, enabling rapid containment. JWTs, or JSON Web Tokens, are central to modern token handling. Each JWT consists of a header, payload, and signature compactly encoded in base 64. The header specifies the signing algorithm, the payload carries claims such as subject and scope, and the signature validates integrity. Servers verify JWTs against published JSON web key material, ensuring that the token has not been tampered with. For example, a JWT might assert that the bearer is part of the admin group and expires in 10 minutes. Proper validation of expiration, audience, and issuer claims ensures that JWTs remain trustworthy artifacts in distributed systems. JSON Web Key Sets, or JWKS endpoints, provide the infrastructure for token verification. Authorization servers publish their signing keys via JWKS, enabling resource servers to fetch and cache public keys. This allows seamless validation without manual key distribution. JWKS also supports planned key rotation, enabling issuers to replace keys without breaking clients. For instance, a resource server validating tokens from an identity provider will periodically refresh the JWKS to stay current. This mechanism ensures scalability and agility, keeping signature verification aligned with evolving key lifecycles. Token exchange is a powerful mechanism that allows one token to be traded for another with reduced privileges or a different audience. This is useful in multi-service architectures where a high-privilege token should not be used broadly. For example, a general-purpose access token may be exchanged for a token scoped only to a billing API. By downscoping privileges, token exchange prevents overexposure and enforces least privilege dynamically. It allows identity to be propagated across services while tailoring access narrowly to each context. Confidential clients maintain secrets securely, such as server-side web apps storing client credentials in protected backends. Public clients, such as mobile or single-page applications, cannot keep secrets and must rely on protections like PKCE. Understanding this distinction prevents insecure design where public clients attempt to hold long-lived secrets. For example, a web server may use client secrets and authorization code flows, while a mobile app relies on PKCE instead. By respecting the difference between confidential and public clients, developers align with security assumptions baked into OAuth and OIDC. Front-channel versus back-channel communication introduces different trade-offs. Front-channel flows, such as browser redirects, involve user agents and are subject to visibility and tampering risks. Back-channel flows occur server-to-server, providing confidentiality and integrity. For example, the authorization code itself travels through the front channel, but tokens are exchanged in the back channel. Designing flows to keep sensitive artifacts in the back channel, wherever possible, reduces risk. Recognizing which channel carries which element is critical to evaluating privacy and security posture. Single-page applications illustrate these challenges vividly. SPAs often cannot securely store tokens in browser local storage, which is vulnerable to cross-site scripting. Instead, best practice favors a backend for front-end pattern, where the SPA communicates with its own server, which manages tokens securely. Same-site cookies further reduce exposure by limiting where tokens are sent. For example, a banking SPA may avoid exposing JWTs to browser JavaScript, instead relying on cookies scoped only to its domain. These patterns demonstrate how architectural choices directly influence token safety. Session revocation and logout strategies ensure coherence across distributed systems. When a user logs out, server-side sessions must be terminated and refresh tokens invalidated. For example, an enterprise identity provider may revoke tokens centrally, cascading logout to all relying applications. Without coordinated revocation, users may believe they are logged out while tokens remain valid. Strong logout strategies ensure that identity controls remain aligned with user expectations. reducing risk from abandoned sessions. Standard error codes and redirects improve resilience in OAuth and OIDC flows. Clear error messages such as invalid grant or invalid scope provide clients with predictable recovery paths, while redirects ensure user experience is preserved. For example, a client that receives an invalid token error can initiate reauthentication without guessing at the cause. Standardization prevents fragmented handling and supports interoperability across diverse systems. It also avoids accidental information leakage that attackers might exploit. Threats to OAuth and OIDC flows include code injection at redirect endpoints, token leakage through logs, and misuse of open redirects. An attacker who manipulates redirect URIs can intercept codes or tokens. Logging tokens inadvertently exposes them to anyone with log access. Open redirects allow adversaries to pivot users to malicious destinations. Threat modeling must account for these scenarios, ensuring that design and deployment controls neutralize them. Recognizing these risks underscores the importance of securing both application logic and supporting infrastructure. Hardening techniques provide the safeguards needed to counter these threats. Exact redirect URI registration prevents attackers from substituting malicious endpoints. State parameters and nonce values defend against CSRF and replay and flows. Strict transport security enforces TLS, ensuring tokens and codes are never sent in plain text. For example, an OIDC client may require that all redirect URIs match registered values exactly and validate state on return. These practices ensure that flows remain resistant to common manipulations. Compliance and audit logging ensure that identity operations remain accountable. Logs should record user consents, granted scopes, token issuance, refreshes, and revocations, all tied to synchronized timestamps. For instance, an audit log might show when a user consented to share profile data with a partner app, when the tokens were minted, and when they were revoked. These records provide defensibility in audits, support investigations, and reinforce transparency. Logging identity events is not optional but fundamental, proving that token handling remains consistent with policy and regulation. In summary, resilient application identity emerges from selecting the right OAuth and OIDC grants, binding tokens to risk, and enforcing strict validation. Authorization code flows with PKCE provide strong user authentication, while client credentials flows secure service interactions. Tokens are scoped, short-lived, and validated for audience and issuer. Rotation, revocation, and storage best practices reduce risk from theft. JWKS endpoints and signed JWTs ensure integrity and verifiability. By anticipating threats and applying hardening, applications transform identity into a defensible, auditable foundation. The outcome is cloud software where trust is provable, tokens are reliable, and identity remains resilient even under attack. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.